So this second part will be shorter, but as I said, we will now bear the fruit of the formulation that we've done. So let me tell you first, before we go on, what is the ultimate thing that you're going to come up with and what you're going to take home is an ability to compute the expectations that I showed you before. Remember I showed this equation that said you sum over all possible parameterizations, and for each one you assume it, you compute the answer to the query, and then you weigh by the probability of that. The end result today will be kind of an efficient way to do that. And the interesting news is going to be that you actually do not really need to do that sum. In fact, there is a special type of point estimates that if you find and plug in the Bayes network and do the computation with respect to that single parameterization, you're going to get back the same answer. The same answer that you would have gotten if you were to do the summation and weigh by the probability. But that works only under complete data, right? So anyways, that's going to be the ultimate that you're going to get today, but there will be ingredients for that. And the other thing you're going to get is we're going to compare this with the map estimates and the maximum likelihood estimates. That's going to be the final conclusion. Let's look more broadly, the bigger picture. You have a data set, and our goal is to compute the probability of observing a smoker who exercises. So that's what you want to know is the answer to this query. The maximum likelihood approach, what did we do? We said, first of all, get the data set and estimate the parameters of the structure. That's what we call them, theta ML, maximum likelihood, based on the given data. And then we plug these into the network, correct? And then computed the probability of that query. And in this particular example, by the way, if you look at, we had 3 particular parameter sets, each had 2 values. That's 8 possible combinations. So we really had 8 possible parameter sets. If you look at the maximum likelihood one, it ends up being this one. This, and out of the 8, this ends up being the one that maximizes the probability of the data set. That guy, you plug it in the Bayes network, you compute the probability of this query, you get that. Now, if you were to do the Bayesian approach, there are 2 ways. The one that I told you, where, let's go back here, where instead of using a single guy, you try every possible guy, right? Each one of the 8. And you compute the answer to this query, and then you weigh the 8 answers by the probability of each one of these guys given the data set, right? This is what I told you. Okay. You will get the same result. I'll give you 3 ways of getting the same computation. This is the one. You will get the same result if you were to take your meta network, which had 5 instances. The data set in this case had 5 examples, right? So we had H1 through H5. You add a 6th one, and then you ask this question. Given the data set, which sets the value of 1 through 5, correct? What is the probability of S6 being S and E6 being E? So this is a question purely on the meta network. I assert evidence on the first 5 slices, and I ask question on the 6th. This is the same as what I already told you. That is, walk over every possible parameterization, plug in the Bayes network, do the computation, and weigh. They're the same. And eventually we're going to do neither. I'll show you the shortcut for that. That's going to be one of the main outcomes of this part of the discussion. Okay, let me see. I think that's the equation. Okay, here's the equation that shows the equality between these 2 guys. This version of it gives you the feel of it, the spirit of what's happening, right? I'm trying here to compute the probability of some alpha, and based on some data sets. So this guy says, iterate over every possible parameterization, compute the probability of alpha under each parameterization, but weigh by the probability of that parameterization given the data set. That's the Bayesian feel of it. It's the same as this. That's the same as doing one inference on the meta network. So if you happen to land on some magical box that can do inference efficiently on meta networks, then you're in heaven, right? That's it. You just do this. But as I said, the highlight is I don't have to do this, which is costly. Look at the sum. I don't have to do this because the meta network kind of complex, there is a shortcut. And the shortcut is, once more, there is a single theta, one theta, that if I plug into the Bayes network, will give me the same answer. And the single theta can be obtained if you were to get the posterior on the parameter set. So we're gonna get to that next. Again, two more things are left. Is how to show you this. What is that magical theta that gives you the same effect, and then a comparison between map estimates, ML estimates, and Bayesian estimates. Okay. Okay, but this is just a concrete example of this previous equation that we've seen this. Okay. This is the magical estimate that if you had your hands on it, then you plug it into the Bayes network and you get the same effect. Again, all of this is assuming the data set is complete, and this is known as the Bayesian estimate. Before we go through the equation, it's more innocent than it looks. This is the expected value. So if you have a distribution, right, you find the expected value of the distribution, that's going to be it. So we're going to find the expected value of the posterior over parameter sets. Okay, but let's look at it notationally. This guy here is what? A parameter set, correct, for the variable x, given a particular instantiation of the parents, correct? This whole thing is what? Is the posterior. The posterior distribution over that parameter set given some data, right? Simple. I'm going to use this posterior to compute the expected values over parameters. Let's look at this. This guy is a vector, correct? So let's say this guy has 3 different values. This parameter set has 3 different values. That's 3 different vectors. If I want to compute the expected value of the first component, what do? I go to each one of the first components and multiply it by the probability of that vector. And that's what's happening here. Look what's happening here. The whole point of this equation is to compute the expected value of a particular component of the vector. Now, look here. It's small x. Small x meaning one of the components in the vector. I'm trying to find its expected value. What do? I sum over all possible values of the vector, of the parameter set. So I'm looking at the parameter sets one by one. For each one, what do? I look at the value of this component of it and multiply it by the probability of that parameter set. Just an expectation. I'll show you in a concrete example in just a little bit. Really, these equations are simple. You just have to get through the notation, right? And we will call this the Bayesian estimates. And you will see that these Bayesian estimates, if you plug them in the Bayes network, you will get the same result as if you were averaging. So what is left here is, I'll show you a concrete example, but then you're going to tell me, wait a minute, how do I get this guy? I need this guy. I need the posterior. That turns out to have a nice closed form. Why? Because of the naive Bayes observation we made, right? And you'll see this in just a little bit. Okay, this is the result that I told you, that if you take these Bayesian estimates, plug them into the Bayes network, that's the same as this guy, the same as summing over all possible and averaging. Okay, this is the main observation here under, don't forget, complete data. The data must be complete, otherwise this is not going to happen. Very good. Okay, 2 more things. The closed form for the posterior, which will finish this, and then you can go implement it, and then a concrete example. Look at the nice closed form for the posterior. This is what we're after, right? You have a parameter set, you have a complete data set, and you want to compute the posterior on the parameter set given that complete data set. Okay, look at it. What is that? That's the prior. Okay, that's simple. You pull that from the CPT of the meta network, correct? This guy here. What are we doing here? Look what are we doing. Iterating over x, small x. What does that mean? We're iterating over the individual components of this vector. What am I doing? Taking the value of that, raising it to what? How many times did XU appear in the data set? That's basically it. Okay, let's parse it again. This is straightforward. This is from the CPT. That's the prior on that parameter set. And here I'm going over every component of the parameter set, raising that component to how many times XU appeared in the data set. That's the posterior. Why did we get this? This is the naive Bayes. If you look at the naive Bayes and do the naive Bayes manipulation, you get this derivation. Let's see a concrete example. Okay, here it is. We're talking about this parameter set. It had two values, either 50-50 or 75-25. These are the two guys, right? And the prior was uniform. So 50% over this, 50%. Okay, so these are two. Here's the data set. So now I want to compute the posterior on this guy, given this data set, and assuming the prior was uniform. We're good? What does the equation says? The equation says this. That's what I'm trying to do. I want to compute a posterior over this and posterior over that. This is what this guy says. The posterior over this, given a complete data set. Okay, this is a normalizing constant. The prior, 50%. Iterate over the two components. First component is 50, the second component is 50, 50-50. Now, what does this first component refers to? E, true, correct? And H, false. How many? E true and H false, how many? Just one out of 5, correct? That's this exponent here, 1. Now, what is the second component of this guy refers to here? What is that? E, false, correct? And H, false. How many? H false and E false, how many? Last two guys, correct? That's this exponent here, correct? Now, same exponents will appear in the second equation. What's the difference though? The difference is instead of 50 and 50, I'm going to put 75 and 25. That's what's happening here. Okay, that's basically the posterior. You normalize, this is the posterior. So, for this parameter set, which had two values, the prior on those two parameter set was 50-50. Given this data set, what is now the posterior? 72.7, 27.3. And that's the equation. Very simple counting. And you can look at the derivation in your book, just using nothing but equations of naive Bayes. Pretty nice. This is one of the more celebrated equations in Bayesian learning. Next time I'll show you the continuous version of this with the Dirichlet. Okay, we're not done here because what did we do now? We just computed the posterior. What do I want? I want the expected values, which are the Bayesian estimates. I think that's on the next slide. Okay, here it is. Look, here's the posterior. The posterior is, on this guy is that. The posterior on this guy is that, correct? If I want to compute the expected values, what do I do? I look at, first I want to E true given H false, right? These are the first and the second guy. I multiply this by that, and I multiply 75 by that. That's what I'm doing here. That's the expected value of the first component, correct? Similarly, the expected value of the second component, I take the 50 by this, 25 by that. That's what's happening here. That's the Bayesian estimate. So for this parameter set, there's two possible values. Each has its own probability, but the expected value of that parameter set is 57.43. We're good? You do this for every parameter set. You take these guys, plug them into the Bayes network, do your computation, guaranteed you're going to get the same result as if you were to do averaging over all possible parameter sets. Pretty nice. So look what we have now. How many different estimates we have? We have maximum likelihood estimate from last time. We talked today about map estimates. And now Bayesian estimates, right? Three different things. So we'll look at tying two of these together. I think this is coming next. Yes, let's look at this. Is going to be our almost last slide. Important slide. Map estimates. What are the map estimates? Here's the meta distribution. I am doing this. I'm finding the parameters that has the highest probability given the data set. Map estimate, just like a map query, correct? Guys see that? Okay, that's this guy. And when the data is complete, we've already seen that this guy decomposes So I can actually do this by simply optimizing each individual parameter set. That's pretty nice. Okay, that's one observation. And these are the map estimates. Now we're going to tie map estimates to maximum likelihood estimates, because this is a very fundamental distinction. Map estimates, I optimize this. ML estimates, what did I optimize? D given theta. Right? I want to find the theta that makes the probability of D highest, correct? How are they related? Bayes rule. Look at this guy. What does Bayes rule says? This, correct? Theta given D is D given theta, which is proportional to that. Now, this is a constant. Let's get rid of it. Doesn't matter. So what is happening here? This, proportional to that. When I'm doing map, I'm optimizing this, correct? When I'm doing ML estimates, I'm optimizing that, correct? What's the difference between the two? Just this. If this is uniform, then it washes out. And this and that are the same. The only difference between map and ML parameter is in the prior. If all network parameterizations are equally likely, that is, this guy is uniform, map and ML estimates coincide, this and that are the same. And both of these are point estimates. The Bayesian approach says I don't want to commit to any, I want to try them all and average and weigh by the probability. Your chapter, I'm going to just show you one more slide to give you a flavor of, there's a lot of material in this chapter that we're not going to go over. Why? Because it's all really inference and approximate inference stuff. Some of it is stochastic sampling, which we didn't go over. There's not much learning. The learning part is done. Right? And I'll just give you a feel of that next. But let me give you an example. When the data is incomplete, you're going to get this, you're going to still do the same computation, you want to evaluate this. Most of the stuff in your book about how to do this by doing approximate inference. The math equations are all done as far as the learning. Look, I'll give you an example of one of the techniques people use to just see this, how you suddenly transition from learning to inference. Right? Look at map. This guy. You can imagine that doing this is easier than averaging, because this guy is looking for one guy as opposed to averaging over all of them. Look what people do. Suppose your distribution is spiked, posterior, end up being centered on one particular parameter set. What does that mean? That means the map estimate is a good approximation of the averaging thing, of the Bayesian. So in fact, some of the techniques just do that. They identify cases under which you would have a kind of a spiked posterior, and then they would use the map estimate as an approximation of the Bayesian estimate. It's all observations based on inference techniques. I want to make one more remark before we leave. One of the beauties of this meta-network business is the following. You can do all kinds of things. So I'm giving you one example we did actually in my group based on this. When you get the data sets, like here's one of them, and you have something that's unknown, right? So typically, what does this say? Say, I don't know whether the first individual is health aware or not, and then I don't know the second one, right? And the assumption here, these are all independent examples, right? Now, suppose someone comes and says, you know what? No. I really don't know whether the first individual is health aware or not, and whether the second, they're health aware. I don't know that. But whatever that is, they're the same. Maybe that's a couple. They're either both health aware or both not health aware, but I don't know which is which. That's more information. I still don't know the value, but whatever that value is for the first example, it's the same for the second example. Okay, it's just one example of additional knowledge you may have. In fact, we handled that particular type of constraints, and you know how you can deal with this? You augment your meta-network to capture this kind of thing, and then you do the mathematics. You just do inference and on that new guy, and then you have a new learning approach for learning with data sets in which you have these, we call them equivalence constraints, right? This is one of the rewards you get out of understanding this at this particular level. And that particular example that I've mentioned is in one of the papers. If someone is interested, I can point you to it. It's not in your book. Okay, so folks, here's what we're going to do next time. We're going to run a version of the same thing, but where the parameters are continuous. And then we will end up talking about a fundamental type of distribution called the Darwiche. The Darwiche is the distribution people use to communicate knowledge about continuous parameter sets. That's a fundamental. But you'll see it will be very intuitive. And then you will get a version of this for the continuous case, which is the more commonly used in practice, right? And hopefully you will have a very solid intuitions about Bayesian learning. So I will see you next time. Thank you.